In this lecture, we're going to be talking about calculating probabilities with the standard normal distribution. So let's get started. And right here, this is a graph of the standard normal distribution, and I want to look at this graph and I want you to notice some things about it. First off, notice that it is symmetric around 0. Okay, we take a look at it, and if I were to be able to draw a straight line coming up there, it would cut it exactly half in two. Also, I want you to notice that that's its high point there in the middle. It goes down after that, and by the time we get to 3, there's hardly anything going on here. It's just very small. Also notice it's a bell-shaped curve. Okay, whenever you hear people talk about the bell curve, this is the one they're talking about. We have this marked across the bottom here with a Z, okay, and this is connected with the Z-score. Whenever we've standardized data before and used a Z, it's actually with an I ahead of applying it to this variable. And we interpret each of these units out here to be a standard deviation, and so right here, so 3 standard deviations away from the mean. Not very much is happening probability wise. We use this curve in order to calculate probability with the normal distribution, and the calculation is connected to the area underneath the curve. So if there is not very much area underneath the curve, that means the probability is very low. Now, I want to talk about, and we talk about the normal distribution because it does come up in connection with real data. This is some real data I've been using. I started off the course with it. This is data. Everybody who comes into my office for a program that I administer, I have them write down how many hours they have. And so the purpose of the program is to help them get graduated and get finished. And so I want you to notice here how many hours. So these people down here with these few hours, okay, they're not so worried about being graduated yet. And in particular, these down here, I don't even know how those got here, because by the rules of the program, you have to have at least 45 hours before you can talk to me. Now, also notice that even though, wow, we've got somebody up here with 220 hours, shouldn't be so many that big, because once you get to a certain number of hours, you graduate. It takes 120 hours to graduate. Now, in this particular data, it has a mean of 108.7 and a standard deviation of 32.5. Okay, and there are 163 data pieces altogether. Now, the median, or excuse me, the mean actually occurs right here. Okay, right. So it is just about the exact middle. Okay, so median is the middle, but the mean is the average. So here, the median and the mean are pretty close together. Let's take this. I'm going to use the mean and the standard deviation to break it down into categories, and I'm going to graph it. And so this is what a histogram of this data looks like when I've broken it down into categories using a standard deviation. Okay. Now, take that picture, and I'm going to juxtapose it here with a normal curve. Okay. These points here are all taken off the formula for the normal curve. Okay, or this right here would be the mean. And I've given them this normal curve the same mean and standard deviation as our original data. And notice here that it's not a perfect fit. We've got this spot right here where it overshoots, this one where it undershoots. But in terms of exact fit, it's not bad. Really, this is the way statistics is. If you get too good a fit, you begin to get really suspicious. Okay, so in order to calculate with the normal, we will refer to a table. Okay, and the probability of the events are areas beneath the normal curve, but above the interval that describes the event. The table that we will be using gives values for events that are of the form 0 to b. Okay, so things above that a little interval between 0 and b. And so we're going to have to massage the table to get everything we need out of it. Okay, and so this is what the table looks like. Okay, and this graph here, this point represents the upper end point, and these numbers here, okay, encode an end point. What it is, these numbers on this side gives me the 1s and the 10s digits associated with whatever that endpoint might be, and these numbers over here, they give me the hundredths digit. Okay, so look at that table. Look here down at the bottom. In particular, the bottom row. It's all like 0.4987, 0.4987, 0.4988, 8889. So all of it is just pretty darn close to 0.5 when we get out that far. So when we get out to 3, we have an area of almost a half, right? This whole curve from here to if you take it from here to infinity, has an area under it of 1/2. Why? Because it's symmetric, and because the area under any total probability curve is going to be exactly equal to 1. Okay, and so we'll be using that fact among others as we go on. Okay, so let's first off, we start out with just a simple example. If you can't do this, you can't do any of it. Okay, and it's not hard, and you need to try at it, but if you can't get over finding out what this is, you're not going to be able to calculate anything with the normal. So let's just start out. Calculate the probability that z is between 0 and 2.34. And so again, this particular formula, the 0, right, it's that point right there. The 2.34, okay, it's that point right there. The number we're looking for is this area in black. All right, and so we break down the number into two pieces. First, the 1s and the 10ths, 1/10. Okay, the 2.3, we go down here. And then for the 0.04, we go over here. So we look where this row meets this column, and it meets it in the magical land of 0.4904. And that is the answer that we write down, 0.4904. Okay. Right, so this is the major diagram. Know what everything it means. Okay, it's all chopped out for you here. Take it, chew it up, make it a part of you. Okay. Okay, example 2. What is the probability of negative 2.34. Less than z, less than 0. Well, here we come in and we say, well, this is not our standard thing. It's backwards, okay? Because in our standard table, 0 is the low end. But what do we know? We know that our curve is symmetric, and so we can just flip it over and get the same area. And then, okay, just do the same table lookup as we did before. So if it has 0 as an endpoint, it's going to be just a table lookup. Here, though, with the negative number over there, realize what you're doing as part of your calculation is using the symmetry of the curve. Okay. Okay, 3. Now this one is different because, okay, it does not have 0 as an endpoint. And so we're going to have to be a little bit clever to do this. What we do notice, though, this is a negative number, and this is a positive number, and so 0 is somewhere between them. Okay, so we take here, this would be, okay, the low end right here. Okay, this is the low end, and this right here is the high end of the interval. So we've got the negative 1.22, we've got the 1.74 right there, we've got the 0 between them. So what we do, we take our mathematical scissors and we cut this in two and put one half of it over here and the other half of it over here. So our total area up here is these two areas added together. Okay, now I've got the 0 at the end point, and so I can find the area just by a table lookup. Okay, over here got the 0 as an end point, and I can find area as a table lookup. And then to get my original area, I would just plop these two pieces back together. So to get my final answer, I add those two numbers together and get this right here. So when I have 0 between the two to begin with, I'm going to be adding two numbers together. Okay? 0 between, you're going to be adding two numbers together. Example 4. Okay, again, I do not have 0 as an endpoint, and here both of my numbers are positive. They both have the same sign, and 0 is not between them, so I'm going to have to do something a little bit differently. Oh, what to do, what to do. Well, okay, so I start off, okay, with okay, a positive number on this end and a positive number. Let's see, that's the wrong spot. It goes over the bigger one there. And a positive number on the other end, it goes over there. I always look up the number with a bigger absolute value first, by the way. That's just a good habit to start. But, so I have it over there. What happens? Well, I want to have a 0, so what do? I take this and I fatten it up. Okay, I add this down, so I get this area here that does have a 0 at the end. Okay, and so I've got this, and it's too much. Okay, how much too much? Well, it's too much this part that I added between here and here. Well, which is this right here. So this is the part I added. So I look up how much the area that I added. It's this right here. And so I subtract it out of the too fat area. I fatten it up to something that's too fat, and then I trim that fat off. Okay, and so I subtract. So when a 0 is not between, I'm going to subtract. When I do not have a 0 between the end points, I subtract. Okay. Example 5. 0 is less than z. Okay. What in the world? Well, what we have here is 0 is less than z. Well, it's just everything on this side. And so if I really want to put it in a three-piece inequality form. I can add this top piece and call it infinity, and I can do it like that. And I can say, okay, the table lookup for infinity is 0.5, right? Because remember, when I looked at that original table, I looked down at the bottom, when I get to 3, it gets to 0.4988.49, and just gradually, it's so close to 0.5 then that why the hell bother with so much difference? It's just such a small difference. So we have a 0.5 here for this z greater than 0. Okay. Example 6. Okay. Well, it's z greater than 1.74. Okay, let's think about this. So z greater than 1.74 is, okay, we've got like the 1.74 here, and it's this little tail. These are called tails. Okay. And so what do I do to calculate this? Well, okay, I fatten it up to be the whole side now, and I know the whole side is 0.5. And then I say, okay, how much fat did I have to add? Well, the fat I added was from that point to 0. And so I just do the table lookup there, and then I subtract the fat out.